Sure. Okay, number 12, rigid body statics. So it looks something like this. There is a circular beam that's connected to the wall by a ball and socket joint. And there is a sleeve in the middle of this beam. With a downward force applied to it of F. And at the end of the beam, there's a cable. And it connects to a pulley. That's a terrible drawing of a pulley. And the coordinate axes, we have the x-axis like this, the y-axis up. Nope, that's the z-axis. The y-axis comes straight out of the beam. Okay, and then a cable goes through that pulley and it connects to the wall in two places. If you go over 4 feet along the x-axis and up 5 feet, you get to one of these points. So this is 4 feet. This is 5 feet. And the cable comes from the pulley to that point. And the other end of the cable if you go straight across into the words, 4 feet on the other side, so that's also 5 feet up, 4 feet across, and the other end of the cable from the pulley goes to that point. And then we know that it's 5 feet from the end of the beam to where the force F is applied. And another 5 feet to the end. And we know that this distance is Okay, and the joint with the wall is a ball and socket joint, and we have to come up with the reactions. And one thing that's different about this problem than the other ones is if you just imagine what's happening here, we're not going to be able to come up with numbers for these reactions. We're gonna come up with reactions in terms of that parameter F. If that force F is really small, those reactions are going to be really small. And it doesn't say anything about masses, so we're actually ignoring the weight of this thing. And so if F was 0, there'd be no reaction forces at all. If F is really big, the reaction forces are going to be big. So we're going to have F in our answer. Okay. So if I draw this from the side in order to imagine the geometry, that cable that comes from the end is going to make a straight line to the wall, where this distance is 5 feet. And the pulley here is 2 feet from the end. This is 5 feet. This is 5 feet. And so we can use that to figure out what the coordinates are of the point where the pulley is. All right, well, let's name some points and come up with the coordinates of these points, because we're going to have unit vectors that represent the directions of those pulling forces and stuff like that. So I think that's a good place to start in a problem like this. Deal with the geometry first. You know you're going to have to do it eventually, get it all in one place. So I'm going to name, so I'll, the origin is the, where the ball and socket joint is. Oops. I'm going to call where the force F is applied B, the end C, the pulley D, and then the 2 points with the wall I'll call E and F. And thinking ahead, just so I don't forget to mention this later. So in this problem, we were told what the origin was of the coordinate system. I mean, we could overrule that if we want, but this is a good choice of origin because if you calculate the coordinates of every one of these points where forces are applied, those coordinates are the row vector, if that's your about point. So if you have the origin of the ball and socket joint, that's a really natural place to put your about point because there are 3 unknown forces there. And so put your about point there, and then the row vectors come directly from the coordinates. It's a nice thing when it lines up. It's not always the way to make your decisions, but it can cut out some steps sometimes, often. All right, so the point Oh, I guess I was thinking was that this origin is equal to A. Okay, so A is the origin. B, to get from the origin to B, you just go 5 feet in the positive Y direction. And we can do this calculation in feet. C is 0, 10, 0. Yep. Now D, we have to do this geometry. We know that you can think of it as, these are similar triangles. This big triangle here and this smaller triangle here are similar triangles. So like if we're trying to find, well, the y coordinate of where this pulley is just 10 minus 2, 8 along the y-axis. But the z coordinate, the coordinate up, if I call that, so I'll call that z. We know that z over 2 is equal to 5 over 10, because those are similar triangles. You could also use inverse trig, find the angle, and it takes a couple more steps, but you get the same answer. But that means that that z coordinate of the pulley is 1. So the point D is at 0x, 8y, 1z. Please stop me if there's anything I say that you don't see. And now all we have left is E and F. For E, it's positive 4 in the x direction and positive 5 in the z direction. So 4, 0, 5. And then F, it's symmetrical, so that's 4 in the negative x direction and 5 in the positive z direction. Negative 4, 0, 5. Any questions about that? Okay, so now all these key points in this problem, we figure out the coordinates. Now let's draw a free body diagram and figure out, what moments we have to calculate and stuff. So free body diagram of the beam. And I'm going to do this too. How am I going to do this? So I guess it depends what cable tension you want to calculate. We could treat, so if we want to calculate the tension in this little bit of cable from here, then we don't even have to deal with that cable going through the pulley. If we wanted to calculate the tension in the cable that goes through the pulley, then we would want to isolate the beam, including that little bit of cable, including that pulley. So is there any reason to, it seems to me like we might as well just, everything's symmetric. We know that the direction that cable is going to pull is straight in the YZ plane. Do you see that? So I think we should be able to solve it by just isolating the beam and treating that as a cable that's exactly in the YZ plane. Okay. So a free body diagram. So there's the beam. We have a cable tension T. We have a force F. And then what loads are applied by the ball and socket joint? Ball and socket applies loads along every axis. So we have a full unknown vector, I'll call that R, and no couples, because ball and socket joints allow every kind of rotation. So now, before we start figuring out the forces and the moments, let's figure out how to represent that cable tension with only one variable, that being T. Okay. We know that it's pointing in this direction from the tip of the beam to that point on the wall, and we know that its x component is 0. Okay. So for that cable force, let's first come up with a vector that's in the right direction. Then we'll normalize it and then multiply it by t, and that'll give us our force vector. So a vector that's in the correct direction is, we can think of it as this point minus this point. We actually didn't figure out that point. Let's just think of it as like, so it's going -10 in the y direction and 5 in the positive z direction. Okay. So this vector u is going to be 0, -10, +5. So 0, -10, +5. The magnitude of that is square root of 125. Which is 11 point, barely more than 11. Or 5 times square root of 5. Can someone give me a decimal for that? Okay. And then, so our unit vector is 0, -10 over 11.18, +5 over 11.18. And what do you get for those decimals? Okay. Oh, and then half of that, 0.445. And so then that force vector applied by the cable is this times t. So 0, -0.890 t, +0.445 t. And so now if I write out rho force moment. So first, let's do the force R at the ball and socket joint. The row vector for R, I'm going to choose, like I mentioned before, I'm going to choose my about point at the origin there. So the row vector for R is 0. The force vector is Rx, Ry, Rz. And the moment is 0, 0, 0. And next I'll do the force F. So the row vector for F is -4, 0, 5. Oh, that's not the point F. That's the point B, 0, 5, 0. And the force is a magnitude of F in the negative Z direction. So 0, negative F, 0. Nope, negative Z direction. Anybody know how I caught that right there? What I noticed that. So I first put it down as 0, 5, 0 with a force of 0, negative F, 0. I know I have to take a cross product between those two, and what happens if you take a cross product between two parallel vectors? It comes out 0. So like when I saw that, I thought like, oh, does it really make sense that that force is going to produce 0 moment around our about point? You know. And then the cross product is negative 5F, 0, 0. And then the last one is that cable force. The row vector is 0, 10, 0. The force vector is this thing we just calculated. So 0 for x, negative 0.890 t for y, and positive 0.445 for t. And the cross product is positive 4.45 t, 0, 0. Okay, that's everything. Anybody have any questions about any of those? So now Newton's second law says Rx, Ry, Rz plus 0, 0, negative F plus 0, negative 0.890 t, positive 0.445 t is equal to zeros. All of those equations tell us something, so we're not going to get rid of any of those. And then the moment equation, rotational Newton's second law, says 0, 0, 0 plus negative 5F, 0, 0 plus 4.45 t, 0, 0 is equal to zeros. Do any of those three equations, like, are any of those three equations useless? Two of them are. The y moment equation says 0 equals 0, and the z moment equation says 0 equals 0, and you guys all learned that earlier, so that didn't help us. Okay, so I'll cross that one out and that one out. And now we have four good equations, and how many variables? Four. We have four good equations, and at first you look at it and think we have five because there's an f there. But remember, that f is the parameter that derives the whole thing. That's going to appear in our answer. Okay, our answer is going to depend on that f. So we're going to do this all in terms of f. So now our system of equations says Rx is equal to 0. We can go down to the fourth equation, and we get that T is equal to 5 divided by 4.45. What's that? And it's positive because you have to move it to the other side. So T is equal to 1.12 times F. So whatever F is, T is going to be 1.12 times that. And now we can plug that in and find our Y. So what's 0.890 times 1.12? Basically 1 point. So yeah, I'll just call that 1.00, or I'll just call it. So that's just F. And then our Z is F minus 0.445 T. Okay, so 0.5 basically F. Any questions about that? So, that approach is a useful thing if you don't know what that force is going to be yet. You have, in a design project, like maybe the people working on that force don't know the answer to that yet. They're still working on that. You do this calculations in terms of F, and then you can sort of compare like the, pros and cons for bigger forces, smaller forces, that kind of thing. What if you wanted to solve this by reduced row echelon form? It wasn't too hard to solve by substitution. But what if you had a problem like this that it was way more complicated, and you had a system of 25 equations and 25 variables? Well, what you would do is treat F like it's a constant, move all the stuff related to F over to the other side of the equation by itself. And then you do reduced row echelon form on the matrix the same way. You just have an F in all your terms on the right side. And you can do that in MATLAB. Most TI calculators, but possibly not all, will let you put variables in like that. Or if you happen to, if all of the terms on the right, and I think they would, are related to f, you can just do it as a number and just remember to multiply f onto the answer. But there are a few ways to do that if the system of equations is bigger. Right. So for RZ, okay, so we got 1f minus 0.445t, and 0.445t is half f. So I think that does come out right. Any other questions about that? Any other homework questions? Okay, well, let's go back to centroids. And last time I gave you that integral definition of a centroid in 3D and 2D. And we went through a calculation for a pretty simple shape, and it was still kind of a pain. We'd rather avoid that if possible. And there are three reasons that combine. So three things combine. So we almost never have to do integral calculations of centroids. Do integral centroid calculations. The first one is once you do the integral calculation once for a general shape, you have a formula that you can use for that shape from that point on, you know, an algebraic formula. For that shape for future use. And we saw that with the triangle. I did the integration and I came up with this formula that told us where the centroid was in relation to the length of the base and the length of the height. Second, centroids always lie on lines or planes, if you're in 3D, of symmetry. And then the third one is the sum formulas allow you to calculate the centroids of complicated shapes that are made up of simple shapes. Okay, so first, I'm going to give you a list of formulas for the centroids of some common shapes. And all of these were calculated by using the integral formula. But once you use it once, you come up with these formulas. Now all you have to do is use these formulas. Um, and so, no, I'll give you these. And so for each one of these, I'm going to tell you the x coordinate of the centroid, the y coordinate of the centroid, and the area. The first one is a right triangle. And that's the one that we calculated last time. So if the centroid is here, and I'm going to call this distance x bar, and this distance y bar. And this is the base b, and this is the height h. Then x bar is b over 3. Y bar is h over 3. And the area is bh over 2. The second shape we'll use a lot is a semicircle. That gets at sort of an important point. It is b over 3, but that's because when we did the calculation, I put my coordinate system over here, and so what I calculated was the distance from a point here to the centroid. And that's, so now we have it flipped around. And so when you use these formulas, a lot of times you're going to have to figure out, like, the shape will be flipped from what you're used to, and you'll have to subtract and whatever. Okay, hold on. Okay, so now I want to do this semicircle. And this semicircle has the radius r, lowercase r. The centroid is here, and I haven't talked much about the requirement that it lies on any axis or plane of symmetry yet, but I'll talk about that soon. But you can see that that's an axis of symmetry for a semicircle, and so the centroid has to lie on that line, that center line. And so the only thing that we have to calculate is this distance, and I'll call that y bar. And so x bar, you get that from symmetry. Y bar is 4r over 3 pi. And the area is pi r squared over 2. Then a quarter circle. Again, has a radius r. The centroid is, well, this also has a line of symmetry. So it has to lie on that line. But in this case, I'm going to give you x and y coordinates. So we're going to call this distance x bar. And this distance y bar. R. The centroid is 4r over 3 pi. Y bar, centroid is the same thing, 4r over 3 pi. And the area is pi r squared over 4. Okay, there's two more of these. The next one is a parabola. You can see that's an axis of symmetry. The centroid is closer to the top than the bottom, closer to the wide part than the narrow part. And we're going to define this using this horizontal distance A. And a vertical distance H. And since we have this line of symmetry right in the middle, the only thing we have to calculate is the distance from the apex to the centroid in the y direction, the way we have it drawn. So x bar comes from symmetry. Y bar is 3h over 5. And the area is 4ah over 3. And then the last one is a semi-parabola. So now we're just taking 1/2 of this shape we just did. And I'm going to define its dimensions the same way I did before. So this distance is still a. The height is still h. The centroid is over here. And now we need to define x bar and y bar. So this is the x bar. Let's see. And the y bar, I'm going to define the same way we did before. X bar is 3a over 8. Y bar is the same as it was for the full parabola. 3h over 5. And the area is just half of what we had before. So 2ah over 3. There are some very important shapes that we're going to use all the time that aren't on this list. We don't have any rectangles, and we don't have any circles. We don't have any spheres. So why did I leave those off? Because of the rules of symmetry. So now I'm going to talk a little bit more about symmetry. So symmetry and centroids. In 2D, a centroid has to lie on any line of symmetry. And that means that if you can find two different lines of symmetry for any shape, the centroid is where they intersect. So if you have more than or equal to 2 lines of symmetry, the centroid is at the intersection. So that's why I don't have any rectangles or circles on here. Um, a rectangle has a line of symmetry like this, and a line of symmetry like this. And so the centroid has to be where they intersect. And a circle has infinitely many lines of symmetry. But they all intersect in the same spot. And so the centroid has to be where they intersect. And that spot is just what you naturally think of as the middle of those shapes. You know, we've actually been doing stuff with circles and rectangles, and we never even talked about the term centroid. We just put stuff at the middle. In 3D, the centroid has to lie on any plane of symmetry. And if you can find 3 planes of symmetry, they intersect at a point. So if a shape has 3 planes of symmetry, then the centroid is at their intersection. Am I going to try to draw this? Let's see what it looks like. Okay, so let's say that you have, for example, a rectangular solid. It has a plane of symmetry like this. That looks pretty good. And a plane of symmetry like this. And 1, 2. So the intersection of those two makes a line, and then it has a plane of symmetry like this. That sort of messed it up, didn't it? Well, anyways, the three of those planes meet inside that shape back here, and so that's the centroid. Any questions about that? Okay. And then the last major tool that we're going to use is the sum formula. So I'm going to call this building up complicated shapes from simple shapes. And the idea is like, what's the centroid of a person? You know, that's a complicated shape. But if you wanted to approximate it, you know what I mean? So, yeah, and you can make it as, if you wanted to get more accuracy, you could use more shapes. You could use a million shapes and they could all be tiny little rectangles and you could get about as, you know, you could get within any level of precision that you were interested in. And so from the front, what's the centroid of a person? Well, it's easy to calculate the centroids of all of these individual shapes. And then we would just use this sum formula I'm going to give you to calculate the centroid of the combination of all of them. So the sum formula, so first I'll give you the one in 2D. And what I want you to notice is, like I said, I'm going to give you all these formulas, but they're not that hard to remember if you remember that it's basically like a finite version of the integral formula, of the integral definition. So the xy components of the centroid, coordinates of the centroid, are equal to 1 over the total area times the sum over all the different bodies, and we're talking about n simple shapes, of the area of the individual shape times the centroid of the individual shape. So that's x bar sub I and y bar sub I. And just notice how similar that is to the integral definition. The integral definition said x bar y bar is equal to 1 over the area times the integral of x bar y bar, the centroid of your infinitesimal amount, times dA. Okay. Now we have the finite version of that. Instead of an integral, we have a sum. Instead of dA, we have a finite area a sub I. And then instead of x bar y bar of the infinitesimal area, we have x bar y bar of that individual shape. So everything that appears in there you can think of as coming directly from the integral formula, just blown up to finite pieces. And in 3D, who wants to tell me what the 3D formula is? X bar, Y bar, Z bar. Yep, 1 over the total volume, that's right. Times the sum for n pieces. Yep, volume again, so V sub I. Yep, and then this is X bar, Y bar, and Z bar sub I. Yep. So everything is like, if you had to guess how this stuff worked, it all kind of works exactly like you would think. So let me do an example problem. So let's say we have a T shape. And let's say this distance is 0.1 meters. This distance is 0.2 meters. This distance is 0.2 meters. And this thickness is 0.05 meters. And we want to calculate the coordinates of the centroid. I also sometimes just write that as the centroid of the vector x. One thing you have to do before it makes any sense to talk about coordinates or components is choose a coordinate system. So what coordinate system? Let's choose one that's right on the line of symmetry. So there's the x-axis, there's the y-axis. And so right away we can see that we don't have to worry about calculating the x centroid. We know that it lies on x equals 0. So x bar is equal to 0 by symmetry. So all we have to calculate is the height. And now I'm going to break it up into two pieces. So we have this piece and this piece. I'll call it piece 1 and piece 2. And in our coordinate system, we just have to figure out where the centroids are for each of these two pieces. So here's the centroid for piece 1. Here's the centroid for piece 2. Piece 1. The area is 0.1 times 0.2. So 0.02. Since our origin is at the bottom, all the way at the bottom, what's the centroid? I am doing piece. Sorry. This should be piece 1 is a length of 0.2 and a thickness of 0.05. So the area is 0.1. From the origin that we're using, what's the y coordinate of the centroid? The middle of that rectangular shape in the y direction. 0.1, yep. And then piece 2. Area is 0.2. And to get that centroid, the centroid of that second piece, from the origin, you go up 0.2 just to get to the bottom of this. Okay. And then you go up another 0.05 to get to the middle. Anybody have any questions about that? So to get to the middle height-wise of this piece 2, you go up 0.2 to get here, another 0.05 to get here, so it's 0.25. So y bar for piece 2 is 0.25. The total area is just A1 plus A2, so that's 0.3. And now we'll use the formula that says the total y bar is equal to 1 over the total area times the sum of, so the area of the first piece times the y centroid of the first piece plus the area of the second piece times the y centroid of the second piece. So like this is A1, this is y bar 1, this is A2, this is y bar 2. And you get 0.05, 0.01, so 0.06. 0.06 divided by 0.3. So yeah, 0.2. And so what that tells us is, you know, this thing, it tells us about what we would expect. It's top heavy. And so the centroid is closer to the top than it is to the bottom along that line of symmetry. And now if you're doing calculations involving forces with this shape, whatever orientation it's in, you can apply the weight force from that centroid. Any questions about that? Yes. Which one? Area 2? It's just this height of 0.1 meters times this width of 0.2 meters. Any other questions? The area should be 0.02, yeah. I think that's what. Yeah, right, exactly. And then the total area, so it all comes out right. But yes, let's make it right. So later generations will think smarter than I am. So this is 0.01, this is 0.02. This is 0.01 and 0.02 and 0.03. This one was 0.01. This one is 0.02. So this is 0.006, and this is 0.03, and it comes out the same. Any other questions? Okay, that's it. So see you Thursday. Right, that's right. That's why I didn't change the answer, because I multiplied and divided both by 10, you know. The 2D one?